0.86647.45 millimeter raised to 4. That is the value of I. Now, using the basic relation m over I is equal to f over y. Now, f max is given to you. So, m over I is equal to f max divided by y max, because f is directly proportional to the y. If y is y max, then f is equal to f max. What is the y max? Y max is 225 divided by 2. Please come on this particular tabletop. So, what is y max? This is my neutral axis. Then this distance, as because of symmetry, is y bottom. This is my y top, and this symmetrical section, hence yb is equal to yt is equal to 225 divided by 2. That is the y maximum. So, please come on this PPT. We can find out y max is 112.5. Now, place the value. We know the value of m, that is 8 by 3 w into 1000, divide by the value of I that we have already found out from the previous PPT, that is 31386647.45, is equal to f max 80, that is given to you in the data, y max that is 112.5, and by solving this equation we found that w is equal to 8369.77 Newton. So, now visualize how we have used the concept of symmetry as well as the concept of bending stress. So, now let us come to the next particular given problem over here right now. Two circular beams where one is solid of diameter capital D and other is a hollow of outer diameter DO and inner diameter DI are of the same length, same material and same weight. Interesting observation. Find the ratio of section modulus of these circular beams. Let us be understood the data, first of all, what is given to us, and then let us be understood what we have to find out. The given thing is that two circular beams, out of one is solid and diameter D is that is known to us. Another is of the hollow circular section. Outer diameter is DO, inner diameter is DI. Now, both the sections having the same length, same material and same weight. Find the ratio of section modulus. Our aim is to find out the section modulus of the solid section divided by the section modulus of hollow circular section. So, with this given data, let L is the length of each beam and W is the weight of each beam. Then, weight of solid beam is equal to this unit weight multiplied by the area of section multiplied by the L length. See, what is the weight of the solid section? Let's come to this particular tabletop. For any section, the weight, we have a fundamental formula. Weight is equal to unit weight of section multiply by volume. Now, what is unit weight? Unit weight is nothing but rho into G. That is, this is nothing but density multiply by gravitational acceleration. Now, what is volume? That is nothing but area multiplied by length. Now, clearly observe that this density which is given to us for both the material is same as the weight is same. G is also remaining constant for both the material. So, if we come to this particular PPT, then weight of the solid beam is the rho G multiplied by the area of section multiplied by the L, where area of section is pi by 4 d square. So, weight of the solid beam is the rho into G into pi by 4 d square into L, while weight of the hollow beam is equal to rho G into area of hollow beam, that is pi by 4 do square minus di square multiplied by L, as L is the length of the each beam remaining same. Now, weight of both the beams are the same. So, if I will equate, this is equal to this, because the weight are the same, we can obtain a correlation between the diameter of solid circular section and diameters of hollow circular section. So, if we are comparing both this equation, L, rho and G will be cancelled out, pi by 4 will be cancelled out, and we achieve this square is equal to bracket do square minus di square. Now, the section modulus of the solid section is pi by 32 d cube, while the section modulus of the hollow section is pi by 32 do bracket do raised to 4 minus di raised to 4. Now, if we can simplify this equation, pi divided by 32 do bracket. Now, do raised to 4 minus di raised to 4 divided into two parts. With mathematics, use the fundamentals, do square plus di square bracket over another bracket do square minus di square. So, the section modulus ratio of the section modulus of the solid section divided by the section modulus of the hollow section is equal to, replace the term with the formula pi by 32 d cube divided by pi by 32 do bracket do square plus di square bracket over do square minus di square. Now, this 32 pi, both terms are goes off, this do comes to the stop, and we will obtain the simplified one equation. We know the basic relationship between capital D and this do and di, that is d square is equal to do square minus di square. So, what I did, I divide this dq term into two parts, d into d square. So, this square term is replaced by do square minus di square, and I got d into bracket do square minus di square multiplied by do divided by the same term, two different brackets. First is the do square plus di square, another bracket do square minus di square. So, this term and this term will be cancelled out. We got d into do divided by do square plus di square. Now, but we know that the d square is equal to do square minus di square. We can replace these terms over here. So, here in this term, we are replacing the term, that is d into do divided by do square plus do square minus d square, because what we did, we are replacing the term. See the previous one, that is what we did, di square is equal to do square minus d square, and we are putting the value over here in terms of the di square. So, finally we achieve the ratio of the section modulus between the solid section and hollow section is equal to d into du divided by 2 do square minus d square. Or, now why or? Because we are replacing the term over here in terms of the d and do. Here the same ratio, if you obtain the inversely, hollow section by solid section, because this is the ratio of solid section to hollow section. Now, if you want to find out the ratio of section modulus between the hollow section and the solid section, then this term will be inverted, 2 do square minus d square by d do. Now, if we take these two terms separately, 2 do square divided by d do minus d square by d do, and we got it the 2 do by d minus d by do is the answer of this given section or the given problem. I wish you have understood this solution very carefully. Let us we go to the next problem. Ready for the problem. A water main of 500 mm internal diameter and 20 mm thick is running full. So, what is the given to you? A pipe having, as it is the pipe is there, it is the hollow circular section which has been given to you. In terms of the internal dia and the thickness of a section, means indirectly the outer dia which has been given to us also. The water main is of the cast iron and is supported at 10 meter apart. That means simply supported section or simply supported beam which has been given to us, as this pipe or water main which is supported at the two supports having a length of 10 meter. Find the maximum stress in the metal. Our intention is to find out the maximum stress in terms of the bending stress. The cast iron and the waterway is of 72,000 Newton per meter cube and the 10,000 Newton per meter cube respectively. This is the weight, unit weight of the section which has been given to us. So, now from this given data we can find out the outer diameter, as outer diameter is equal to internal diameter plus 2t. How? Please refer the figure on this particular tabletop. What is given to us over here? A water main, that is the pipe which has been given to us. The water is inside of this section. Here the water is there. Water is passing from this. This is the outer dia which is not directly given to us, but yes, it has been stated that internal dia which is equal to 500 mm and the thickness which has been given to us which is of 20 mm. So, we can find out do is equal to di plus t, that is di plus 2t. So, if we come on this particular PPT, then outer dia is di plus 2t, that is 500 plus 40, 2 into 20, 40, sorry, it is here. So, 540 mm. Now, weight density of the cast iron is 72,000 Newton per meter cube and the weight density of water is 10,000 Newton per meter cube. This is the figure for a section. Now, the internal area of pipe is equal to pi by 4 di square, that is pi by 4 into 0.5 square, and we achieve as 0.1960 meter square. This is also equal to the area of water section, that is the available area for water flowing, that is area of water section is 0.1960 meter square. Outer area of pipe is equal to pi by 4 do square, that is equal to pi by 4 into 0.54 square. So, the area of pipe section is pi by 4 do square minus di square, and we achieve as 0.0327 meter square. This is the area of pipe section itself. So, the moment of inertia of the pipe section about neutral axis is given by an equation pi by 64 bracket do raised to 4 minus di raised to 4. So, pi by 64 bracket 540 raised to 4 minus 500 raised to 4, we achieve 1.105 into 10 raised to 9 millimeter raised to 4. Now, let us find out the weight of the pipe and the weight of the water main for 1 meter length. So, weight of the pipe for 1 meter length of run is equal to the weight density, that is the unit weight of the cast iron, that is the material from which it is made up, multiplied by the volume of the pipe, that is we discussed in the previous problem also. So, it is the unit weight which has been given to us is 72,000 Newton per meter cube multiplied by the volume of pipe, that is the area, cross sectional area multiplied by the length in terms of the meter cube volume. So, because this is Newton per meter square, sorry, Newton per meter cube. So, 72,000 multiplied by the area that we already found out as 0.0327 multiplied by the length, that is per 1 meter run, we achieve the weight of the pipe for 1 meter run is the 3254 Newton. Now, the weight of the water for 1 meter run in terms of Newton is equal to the weight density of water multiplied by the volume of water. What is the weight density of water? Which is given in the data, that is 10,000 Newton per meter cube multiplied by the volume, that is nothing but the cross sectional area multiplied by length. Cross sectional area of water section is 0.196 and the length is of 1 meter, and we achieve as 1960 Newton. So, we achieve two things: weight of the pipe for 1 meter run, that is 3254 Newton, and weight of the water for 1 meter run is the 1960 Newton. Now, total weight on the pipe for 1 meter run, what is the total weight for 1 meter run is summation of both, summation of the weight of the cross section, that is of 3254 Newton, plus the another weight of the water, because water is passing throughout the water main. So, per 1 meter length of my beam, the weight of the given pipe is equal to the weight of the cross section of a pipe, that is the cast iron, and weight of the water, and that is summation of both the things 4313 Newton. Now, the above weight is the UDL on the pipe.